Ever launch a bottle rocket or maybe just watch a basketball like soar through the air?
Mm-hmm.
We're taking a deep dive today into the forces that make those things happen.
Yeah.
It's all about Newton's laws of motion. We've
Yeah.
got a great presentation on the topic.
Right.
And we're going to break it all down for you
Yeah.
so you can really understand like how the world works.
It's fascinating how these laws written centuries ago
Yeah.
are just as relevant today. They're the foundation for understanding motion,
Mm-hmm.
from the smallest particles to the planets in our solar system.
Okay, so to start off, the presentation really emphasizes this idea of forces. It
Right.
sounds pretty basic,
Yeah.
but what are forces exactly?
Yeah.
And what makes them so important?
Forces are basically what cause any change in motion,
Hmm.
starting, stopping, speeding up, changing direction,
Yeah.
all of that.
Okay.
They're a push or a pull on an object.
Mm-hmm.
And the presentation highlights that force is a vector,
Okay.
meaning it has both strength, uh, magnitude, and direction.
So it's not just how hard you push or pull,
Exactly.
but also where you direct that push or pull.
Exactly. Think about hitting a tennis ball.
Okay.
The force of your swing determines how fast it goes,
Mm-hmm.
and the angle of your racket determines where it goes.
Right.
Both are crucial for a killer shot.
Makes sense. And the presentation uses a hockey puck analogy to illustrate this, right?
Yes. It shows how the force of a hockey stick hitting the puck causes it to accelerate and change direction. The harder the hit, the faster the acceleration.
Okay. So we've got forces driving motion, but now let's bring in Newton's laws.
Right.
The presentation calls them the rule book for how all this works.
Mm-hmm.
Where do we even begin?
Well, the first law is often called the law of inertia.
Okay.
It basically says that objects like to keep doing what they're already doing.
Okay.
An object at rest stays at rest. An object in motion stays in motion at the same speed and in a straight line.
Mm-hmm.
The only way to change that is with an unbalanced force.
Hold on. So you're saying if I sent a hockey puck gliding across a perfectly frictionless surface, it would just keep going forever unless it hit something?
That's exactly what Newton's first law predicts. Inertia is the tendency of an object to resist changes in motion.
Mind blown.
Yeah.
Okay. On to Newton's second law.
Mm-hmm.
This is where the famous FMA equation comes in,
You
right?
got it. This law quantifies the relationship between force, mass, and acceleration. The equation tells us that force equals mass times acceleration.
Okay, so let's break that down. More force means more acceleration. Making sense so far.
Right.
But what about the mass part?
Think about pushing a shopping cart. If you want to speed it up quickly, higher acceleration, you need to push harder, more force. But a cart full of groceries, higher mass, will need a bigger push to achieve the same speed up as an empty cart.
So heavier objects need more force to accelerate at the same rate as lighter ones. Makes sense. Now what about Newton's third law? Isn't that the what goes up must come down one?
Well, that's one way to think about it, but it's more general than just gravity. Newton's third law states that for every action, there's an equal and opposite reaction. It means forces always come in pairs.
Okay, I'm a little fuzzy on that. What would be an example beyond just things falling back down to earth?
Imagine jumping on a trampoline. You push down on the trampoline, the action,
Okay.
and the trampoline pushes back up on you with an equal force, the reaction sending you flying.
So every time we interact with something, we're creating these force pairs.
Exactly. And that brings us to an important concept. Net force.
Okay, here's where it gets really interesting.
Yeah.
I've always wondered about that term.
Net force is simply the overall force acting on an object.
Okay.
It's what determines if and how the object will accelerate. Think of it like this. If you have multiple people pushing and pulling on a car,
Yeah.
the net force is the combined effect of all those pushes and pulls.
So if everyone is pushing and pulling in different directions with different strengths, you need to consider all of that to figure out what the car will actually do.
Precisely. The presentation shows this visually, with a red ball and arrows representing forces. If the forces are balanced, meaning they cancel each other out, the net force is zero.
Just like that book resting on a table, gravity is pulling it down, but the table is pushing back up with an equal force, so it stays put.
Yes, that's a state of equilibrium, balanced forces, no change in motion. But if the forces are unbalanced, there's a net force, and the object will accelerate in the direction of that net force.
So that would be like our hockey puck again.
Right.
The force of the stick hitting it is greater than any opposing forces, creating an unbalanced force and sending the puck flying.
And the presentation emphasizes that even a tiny unbalanced force, if it acts over a long enough time, can lead to a significant change in motion. Think about a tiny rocket engine continuously firing in space. Over time, that small force can accelerate a spacecraft to incredible speeds.
Wow, it's amazing how these forces are shaping everything around us constantly.
Right.
But there's another force that always seems to be working against us: friction.
Ah, friction. The force that opposes motion between two surfaces in contact.
Hmm.
It's always there, acting in the opposite direction of the intended or actual motion.
So friction is like a constant battle against motion.
You could say that.
Mm.
It's caused by tiny irregularities in surfaces,
Okay.
even ones that appear smooth.
Okay.
These imperfections interlock,
Mm.
creating resistance.
Wait, so even a surface like ice, which feels incredibly smooth, has these microscopic bumps and ridges causing friction?
Exactly. And the presentation breaks down friction into two main types:
Mhm.
static and kinetic. Static friction is what prevents an object from moving initially, like when you're trying to push a heavy box across the floor.
And kinetic friction, also known as sliding friction, is what slows things down once they're already in motion.
Yes, imagine that same hockey puck sliding across the ice. Kinetic friction is what eventually brings it to a stop.
Okay, so we've got friction working against us, but we also have gravity, which seems to be constantly pulling everything down. How does that fit into all of this?
Gravity is another fascinating force. It's a fundamental force of attraction between any two objects with mass. And here's the key: it's universal, acting on all objects everywhere.
Wait a minute, so you're telling me that I have a gravitational pull?
Technically, you do have a gravitational pull.
That seems crazy. How come I'm not pulling objects towards me?
It's just incredibly weak
Oh,
compared to, say, the Earth's gravitational pull on you. The strength of gravity depends on two things: the mass of the objects and the distance between them. Greater mass means stronger pull, and greater distance means weaker pull.
so that's why we feel Earth's gravity so strongly.
Right.
It's massive.
Yeah.
But what about that classic example with the apple falling from a tree?
That perfectly illustrates Newton's law of universal gravitation. Every particle in the universe attracts every other particle. The apple is attracted to the Earth, and the Earth is attracted to the apple. But because the Earth is so much more massive, the apple's movement is much more noticeable.
So it's not just the apple falling to Earth,
Right.
but Earth also falls a tiny bit towards the apple. That's pretty wild. And this brings us to a point I always get confused about: mass versus weight.
It's a common mix-up. Mass is the amount of matter in an object, measured in kilograms, while weight is the force of gravity acting on an object, measured in newtons.
Okay, so my mass stays the same whether I'm here on Earth or floating around on the moon, but my weight would be much less on the moon because its gravity is weaker.
You got it. Mass is constant, while weight depends on the gravitational field.
This deep dive is already bending my mind. We've covered so much: forces, Newton's laws, friction, gravity. It's amazing how much is packed into these seemingly simple concepts.
And we're just getting started. There's so much more to explore. In the next part, we'll dive into different types of friction and how they affect our everyday lives.
I can't wait. Until then, let those physics wheels keep turning.
Mm-hmm.
Welcome back to the deep dive. I'm still trying to wrap my head around the fact that I have my own gravitational pull,
Yeah.
even if it's tiny.
It's a reminder that we're all connected in this grand cosmic dance of forces.
I love that. Okay, so before the break, we were talking about friction.
Right.
We covered the basics of static and kinetic friction,
Mm-hmm.
but the presentation also mentions this thing called rolling friction.
Yeah.
What's that all about?
Rolling friction is the force that resists motion when an object rolls over a surface, like a car tire on the road or a bowling ball down the lane.
So instead of sliding, the object is rotating.
Yeah.
Does that really make a difference in terms of friction?
It makes a huge difference.
Right.
Rolling friction is typically much weaker than sliding friction. This difference is why we invented the wheel. Imagine trying to drag a heavy load on a sled versus rolling it on a cart.
Oh, okay.
That's rolling friction making life easier.
Ah, that makes sense. So why is rolling friction so much weaker?
It comes down to the nature of the contact between the surfaces.
Okay.
With sliding friction, there's a lot of surface area in contact,
Mm-hmm.
leading to more resistance.
Okay.
But with rolling friction, the contact area is much smaller,
Okay.
and the surfaces kind of deform slightly as they roll, reducing the friction even further.
So it's almost like the object is constantly lifting itself over those microscopic bumps and ridges instead of grinding against them.
That's a great way to visualize it. And the presentation highlights how we've harnessed rolling friction to our advantage with inventions like wheels and ball bearings.
Right.
They're designed to minimize friction and allow smoother, more efficient motion.
It's amazing how something as seemingly simple as a wheel has revolutionized transportation. Speaking of putting things into motion, I've always wondered how rockets actually defy gravity and blast off into space.
Right.
Is that also related to Newton's laws?
Absolutely.
Yeah.
Rocket launches are a perfect example of Newton's third law in action.
Okay.
Remember, for every action, there's an equal and opposite reaction.
Right.
In a rocket launch, the engine expels hot gases downwards with tremendous force.
So that's the action.
Yeah.
What's the reaction?
The reaction is an upward force of equal magnitude pushing the rocket skyward.
Mhm.
It's literally pushing off the expelled gases.
So the rocket isn't just flying, it's pushing against something to propel itself upwards.
That's right. It's a continuous process.
Okay.
As the rocket burns fuel and expels more gas, the upward force continues to act on it, overcoming the force of gravity and accelerating the rocket higher and higher.
Wow, it's mind-blowing how a principle as simple as action-reaction can achieve such a powerful outcome.
Yeah.
So we've seen how Newton's laws work on things here on Earth.
Hmm.
But I'm curious, do these laws apply to, say, the planets in our solar system?
Newton's laws are universal.
Okay.
They govern motion throughout the cosmos.
Wow.
In fact, Newton's law of universal gravitation explains why the planets orbit the sun the way they do.
Okay, so remind me, what exactly does that law state?
It says that every object with mass attracts every other object with mass.
Okay.
The sun, being incredibly massive, exerts a huge gravitational pull on all the planets in our solar system.
So the planets are constantly being pulled towards the sun.
Right.
Why don't they just crash right into it?
That's where the planet's forward motion comes in.
Okay.
They're also moving at high speeds, and this motion, combined with the sun's inward pull, creates a curved path, resulting in the elliptical orbits we observe.
So it's like a constant tug of war between gravity wanting to pull the planets in and their inertia wanting to keep them moving in a straight line.
That's a great analogy. And the shape and speed of each planet's orbit depend on its distance from the sun and its mass. It's a delicate balance, but it's a balance that's been maintained for billions of years.
It's incredible how these laws create order and predictability on such a grand scale.
Yeah.
I'm starting to see how physics is woven into the fabric of everything around us, from a simple ball rolling across the floor to the planets moving in their orbits.
That's the beauty of physics.
Yeah.
It gives us a framework for understanding the world, from the mundane to the
Yeah.
extraordinary.
Yeah.
And while the concepts may seem complex at first, they ultimately help us make sense of the patterns and processes we observe all around us.
We've covered a lot of ground in this deep dive.
Yeah.
But before we wrap things up,
Yeah.
I'd love to get into some more real-world examples of how Newton's laws are at work.
I think that's a great idea.
Yeah.
Let's see how these laws play out in everyday scenarios and explore some of their more surprising applications.
This is going to be fascinating. Let's take another quick break, and when we come back, we'll delve even deeper into the world of forces and motion. Welcome back to the Deep Dive. We've been exploring how Newton's laws govern everything, from hockey pucks to planets.
Right?
Now I'm ready for some more real-world examples.
Well, let's start with something you experience every day.
Mm-hmm.
Driving car.
Okay.
Have you ever noticed how you feel pushed back into your seat when you accelerate quickly?
Oh, absolutely. It's like an invisible force is pressing me against the seat.
That's inertia at work.
Okay.
Your body's tendency to resist changes in motion.
Mm-hmm.
Remember Newton's first law?
Right.
An object at rest tends to stay at rest.
Yeah.
And an object in motion tends to stay in motion at the same speed and direction.
Right.
When the car accelerates,
Yeah.
your body wants to stay at its original speed.
Okay.
So you feel that push backwards.
That makes sense. And I guess it's the same reason why we lurch forward when the car suddenly brakes.
Exactly.
Yeah.
Our bodies want to keep moving at that same speed.
Right.
That's why seatbelts are so important.
Yeah.
They provide an external force to counteract your body's inertia and prevent you from being thrown forward in a collision.
So Newton's laws aren't just explaining how things move, they're literally saving lives.
Absolutely. Physics is all around us,
Yeah.
often working behind the scenes to keep us safe.
That's amazing.
Now let's shift gears and talk about something a bit more playful. Sports.
Okay, I'm all ears. I've always been fascinated by how athletes can achieve such incredible feats of strength and agility.
Well, a lot of it comes down to understanding and applying the principles of forces in motion.
Okay.
Take baseball, for example.
Mm-hmm.
A pitcher throws a fastball,
Right?
and the batter hits a home run.
Yeah.
Newton's laws are at play every step of the way.
Okay, let's break that down.
Okay.
First, the pitcher throws the ball.
The pitcher uses their arm to exert a force on the ball, giving it velocity and setting it on a trajectory towards home plate.
Mm-hmm.
The faster the pitch, the more force the pitcher has to apply.
And the batter swings the bat.
The batter swings the bat with a certain force and at a precise angle to connect with the incoming ball.
Yeah.
This impact creates an unbalanced force on the ball, changing its direction and sending it soaring into the outfield.
And the crowd goes wild. But it's not just about raw power, is it?
Right.
Timing and technique seem to play a big role, too.
Absolutely. Skilled athletes have an intuitive understanding of how to manipulate forces and motion to their advantage.
Okay.
Think about a basketball player shooting a free throw.
Right.
They have to apply just the right amount of force at the right angle to arc the ball perfectly into the basket.
Mm.
It's a delicate balance of forces and precision.
It's like they've internalized these physics principles without even realizing it.
Right?
It's amazing how much of our world can be explained by these fundamental laws.
That's the power of science.
Yeah.
It gives us a deeper understanding of the universe and our place in it.
Yeah.
From the smallest atom to the largest galaxy, from everyday activities to extraordinary achievements, the laws of physics are constantly at work, shaping the world around us.
This deep dive has been an incredible journey. We've explored the fundamental forces that govern motion, from gravity to friction, and we've seen how these forces play out in countless scenarios, both mundane and remarkable.
Yeah.
I'm leaving with a renewed appreciation for the elegance and complexity of the physical world.
It's been a pleasure exploring these concepts with you.
Likewise.
Remember, physics isn't just about equations and formulas.
Mm-hmm.
It's a way of understanding how the universe works,
Right.
a lens through which we can appreciate the beauty and wonder of the world around us.
Well said. To all our listeners, we hope you've enjoyed this deep dive into Newton's laws. Keep exploring, keep asking questions, and never stop learning.